Hello and welcome back to another session of Looksies. It's Byron speaking, and today we're looking at Rust Doom. Yes, you heard right, it's Rust Doom. I accidentally found this repository, and actually it's quite a massive one in terms of stars. I wonder why I didn't see this before. I just accidentally stumbled over it when studying internals.rustlang.org. But hey, what is it? Let's see. Let's run the release build here. Yeah, and I think we also want to have a higher resolution of 1920 by 1040 maybe. So let's see. I pre-compiled that obviously, and yeah, it's Doom. You can walk on the ground. You can basically get up everywhere. You have animated textures. You have the original lighting. I mean, those of you who are old enough, basically, they will remember exactly that, the feelings will come up, because I've been playing this quite a lot when I was young. And yeah, it looks totally authentic. Also, the banding that happens here with the shadow, with the lighting, it's quite amazing. Of course, for you it might look like 24 FPS or something because I'm recording at 24 FPS. In reality, it's running at butter smooth 60 FPS. And I think the process that does the computation, where is it? Yeah, I think it doesn't even show up. Oh yeah, here it is. So as you can see, it kind of consumes 1% CPU in its loop. So it's really, it's programmed very efficiently, it seems. Of course, it uses modern hardware. It uses OpenGL for acceleration. That's not a software renderer that you see here. And I'm really curious how it's done. I want to try it out. I want to see the code. And of course, we are going to do this before I have to stop myself. One last thing, you're able to define levels here, so I can go to level 8 of the WAD file that I downloaded. There is a link to a WAD file that you can download straight away on the GitHub page of the project. So yeah, I think that's the shareware versions WAD file that I have, which interestingly contains a lot of levels. So here it is. Oh, screenshots, really? I didn't see these guys. Huh. I would love to see these sprites, but not for me. Yeah, I've just built it yesterday, so I believe that sprite rendering is there, but it doesn't show up. Maybe it's because it's a demo version or something. But yeah, what can I do? Can I turn something on here? Somehow I'm trying. Look at this lighting, it's animated. Ah man, so awesome. Nice. I like it. I don't know where the sprites are. It would be great if I could see them, but maybe find them in code. So let's have a look at the structure here, the project structure. So source file wise, there seems to be just Rust stuff going on. Oh no, fragment shaders and vertex shaders. Okay, so once again, I think nothing is done anymore using, I'm kind of an old school guy, and the last time I used OpenGL, old school guy, man, I'm not that old, but last time I used graphics or did some graphics programming, I just used OpenGL calls directly, which probably is not the fastest, but if you use array calls, this is probably a nice thing to have, but nowadays you do it differently. Nowadays you use vertex and fragment shaders, and we will definitely have a look at these. And then there is, so that's the one I downloaded. Then there is a toml file that configures some game stuff. Let's have a look at this. Yeah, maybe I just kill the Java code here. So very nicely documented, and yeah, what stuff that was previously hard-coded, I think, is now configured here in this toml file. Neat. Let me decorations, pool of blood and flesh. So I guess this is kind of an access table. Yeah, just kind of, now I get it, because all these sprite information thingies were hard-coded. It obviously isn't existing in the WAD file that you downloaded. So the asset information is not part of the WAD file. It just contains the data, the dumb data itself, and no metadata apparently. So the metadata has to be put here. Lots of work. Maybe that's auto-generated. So first of all, I believe, usually when I do these let's look at, I see stuff that I can improve. But in this case, I don't think I will be able to improve anything, because the guy who made it is like, whoa, super pro. So first thing, you have one cargo TOML here of the primary project, and you pull in your own dependencies via the path here, which is really interesting, which is a great way, I think, to separate your stuff out into multiple libraries. So sometimes I'm kind of stuck thinking that, damn it, you can have multiple binaries, but only one library per crate, which is, a restriction, but you can work around that restriction by just setting up your own dependencies that use a path, and then you have one cargo TOML per dependency that you define yourself. So here you see, well, we have a single library here which deals with WADs apparently, and you pull in even additional dependencies from the top level again. It's really nice, I think. It's also a great way to separate the dependencies, and I think this is really why you would want to do this. So if you have graphics related, or if you have the game logic itself, it tends to be not dependent on too much, especially not on the graphics subsystem. So probably it's a good thing to signal that and say, well, the game here, it doesn't need that much. Okay, it needs SDL2 apparently, but as you can see, it doesn't need as many other crates as it needs GL as well. Yeah, I'm just saying. I think it's a very clean way to do this, and it's something to learn from, while still keeping everything in one repository. So I think the rest is really just the actual code. We have a main file, obviously, which is the binary that we execute, which I guess does the argument parsing and pulls everything together. So how does that look like? Yeah, so here basically just handles the options. Okay, some option parsing. So you get, and it's always interesting to see how that's done. So you try to access the resolution, unwrap it or default to this string. Then you try to parse it here. Okay, so that's manual parsing. You find X, and this returns an optional position. So X, I guess, is the index of the byte that was found there, or of the character that was found. How is that? I mean, sure, this is ASCII, right? So the byte index is the character index, but technically you would have to deal with UTF-8 here. Practically, I think you don't. So if X is reasonable, use it and basically just get slices here that you will then parse. So that's cool. The mapping, oh no, wait, the and then here, does it change the type? Because this returns a tuple. Okay. Yeah, sure. You have to pack it into a tuple to be able to access it. So here, size 0 is the width, size 1 is the height, and you just parse it as U32. And then, I like this a lot. You get this thing again, but this time as parsed values, which are results, right? And then you match on this and see, okay, if both have parsed all right, unpack it, basically. Use it. Otherwise, don't take it. So if so if there is something, then fine. Otherwise, so now it's interesting. Now we go with error handling. Okay, or else. So either we have something in here, or we map it to a string. What's a general error? So that's common general error. Let's pick it up. Source common lib. Okay, so that's just an error with a string. It can be converted. It can be generated from strings of all kinds. It can display itself. And yeah, there's a custom read extension trait, which is implemented for all T's that are read. So that's interesting. This is how you can attach basically any custom functionality to all types that implement a certain trait. Really nice. All right, so I still wonder, okay, or else. And that's, okay, so that's all in a try, right? But is this a string find returning a result, or is it returning an optional? It probably is a result, huh? Otherwise this wouldn't work with try. String find. No. No? Okay. Probably it's on some trait or somewhere else, or it's an str thing. Okay, see, it returns an optional, and in the middle of it, and that's the interesting part, it becomes a result. So maybe it's the okay or else that does that. I've never used that. So I always find this very, very interesting. Okay or else, which returns a result. See, this is how you change it. So that's very nice. So it's okay. And in any case, the conversion to a result happens. And this is awesome. I was always asking, okay, if I have an option, how am I able to use try here? Answer, you are not unless you do the conversion. And you get a boxed error. So I think boxed error is one way to use try all the time, because there's a general error here. And there is no code here that would convert it into a box for you. But I think this is already implemented for this kind of type, huh? So that this general error returned here is boxed because there is a conversion trait implemented, or the from trait is implemented, that says from general error for boxed general error. And that could be doing it. Yeah, so that's super interesting. So much stuff hidden in these few lines. Answer, is it easy to read that? Is it maintainable? I think yes, once you got the hang of it, of the Rust thing, basically. And okay or else, yeah, so this is the try block here. And yeah, this will just return if there's nothing. Otherwise, you get the width and height with full error handling and error checking. Field of view, same thing here, with a try around it. Okay, and parse returns a result, which, yeah, unwrap or, let me parse it, that is a result, that's what we try on. I didn't know, but that's super useful, that anything that implements error can convert itself automatically into a boxed error, which is exactly what you want to have a generalized error return value. Awesome. So here some more parsing that tends to be the same. Oh, and the error handling is done so that if there is an error, basically you just convert it into your own error, right? So that's the error mapping here. Let's not forget about that. Okay, so here, run mode, play, game config. So here we basically just return the run mode. Okay. Oh, pub enum. Okay, that's interesting. So whichever run mode it is, we return with the respective options. Okay. So that's the play mode. That is the most elaborate one. That's the one we have seen, I think. Okay. So how does it work? Run config not test. Yeah, that's interesting. If you just run cargo test, let's run it, by the way. Cargo test. Then you can get these warnings about unused code. But this is one way, I guess, to not compile this stuff in test mode. CFG not test. Okay, so here we have main. Let's follow it up. Get the args. Collect them into a vector, because by default you get an args iterator. And then you do the parsing here that returns. Oh, interesting. Run mode from args. That's this implementation. I like it. I like it a lot. And then you can just match on it and do what you have to do. So here you unpack your tuple. No, it's not a tuple struct. Oh, I didn't know this works. Oh no, wait. I knew this works, but I never used it myself. So here you can have struct variants, right? That's just a struct variant, which is something that I would use all the time. I have always been using tuple variants because I didn't know better. But with a struct variant, you obviously have the possibility to name your fields, which is better in terms of self-descriptive code. That's nice. So here you basically just match on your struct and unpack it. Then you do what you have to do. Okay, let's do the play thing. So apparently this is some code ripped out elsewhere, because if you play, apparently all this initialization happens in some way as well. And that's what we have to look at next to follow the game along during its initialization phase. So game new, that's probably easy. Run. So source game, what do we have here? A lib, obvious, I mean probably just pulls it all together. Here we are. It does, which is the standard. Shader root, okay, it's nice. Avoidance of magic values in your code. And then I guess in game RS we will find the new and run methods. So here we go. So new does this initialization, gets the window, gets SDL2. If you look at it, it's exactly the same that happens here. I mean, not exactly, but probably pretty much similar. Archive open, so we get the WAD file. We try on everything and return boxed errors, which is awesome. Proper error handling, always, everywhere. Try is your best friend. Get a new player. And set the level start position. Okay, I didn't know these have that, but obviously that's the kind of metadata that is indeed existing in the WAD file. Okay, and when we run it, what happens? Quit gesture, any off. Where's the gesture coming from? Control. Aha. So we can press escape and Oh, that's the grab toggle. So that's the grave. The backtick, I think. Accent grave. Okay. Time, precise time. So it does its own game loop. And let's see. So that basically assures we get a smooth whatever amount of frames per second. I don't know how that exactly works. So here we render the data. So level render is what you want to look at to get that, I guess. And you give it everything that you want to render. Player, camera, information, and that's it with the time delta. Okay. I don't know where the player is advanced or where the input handling is done. And then what else? Frame time. Oh, did it spit out a frame time? No. But I think we can try that. Rust log. Yeah, I forgot. You can have complex descriptions here of what you want to log. I think if you put it to info, frame time, there it is. See, was that easy? FPS 60, cool. Very nice. Woohoo, that totally works. Very nice, even with logging. I never used logging really, because my programs were too simple to justify it, but here, you know, very nice. I love it. You can learn so much from code like that. I mean, look at the standard library, you learn a lot there as well, but this seems to be primarily safe code. Okay, so what else is there? Unfortunately, I can't use the sidebar because I'm not in the project really. Then we have game cached. I mean, there's probably too much, but game level does the rendering here, or some rendering. You might have a look at this. And follow it along a little more. So here we are in the level implementation. That's a bit more. Find thing, build palette, init sky, atlas, decor. Wow. So yeah, it initializes everything. Gets the level from archive. I wonder how that works. Is this a borrow then, a reference to that? Only has to access it read only, right? But maybe not, I'm not sure. Render steps, Sky flats, walls, decors. Shader loader. So here shaders already play a big role. Renderer add steps. So I guess it's like a layered approach or a list approach. So the renderer just steps through the individual items to do, and then remember what you have to remember. And if you want to render, that's render code apparently. Step mut. Add constant for lights, blah blah blah. So for each step you do some configuration maybe, and then you render. Okay. So the renderer is a renderer which comes from GFX renderer. Okay. What else do we have here? Yeah, that's interesting here. That for some reason underscore is used. I've never seen the need to use an underscore for member names because either they are public or they're not, but you usually wouldn't care. And underscore, helps no one really. So I wonder why, or what kind of semantic use, what kind of a semantic it uses here. Maybe it's because of the representation stuff. Because here that's, oh no, wait, that's an enum. So for instance, here, these all are private fields and there's no underscore, but it's also not a C packed structure. So maybe that is why, huh? And we have not seen any C code. I guess this is loading stuff from the WAT file. Like, that's a serialization format, maybe. Somehow. Could be. Offset off, yeah. I think that might be initializing information of how to obtain stuff from the WAT file. Decor vertex. Yeah, that's way too complex to understand just by staring at it. For me, at least. But it's interesting. Now, I mean, you know, whatever happens here, it's good. Points to polygon, that's interesting. So I guess it's some sort of triangulation that happens here. Points sort by. That's also interesting. That's an in-place sort. That at the end returns just an ordering here. Nice. Yeah, what I'm interested in is to see these shaders actually. So the renderer, by the way, render. GFX, where is that coming from? Here. So here we have the render code. It's somehow GFX render. Can have a quick look. Pardon. So here it is. Well, doesn't seem to do much, huh? Go through each render step and run render setup, and render setup does what? Okay, it basically does the shader and that's the shader setup, huh? That's how it seems. It binds the stuff, draws triangles, and that's that. Okay, and at the end, it just clears up its state. Okay, so basically, looking at the shaders is not a bad thing. How is the sky rendered? And how is the sky vertex stuff happening? Okay. So here, yeah, that's really interesting because I have no idea how this really works. Model view. That might be related to the C-packed structures that we have here, because these names definitely relate to stuff that you define somewhere in your code and in your own structure. So let's look for U projection, for instance. Good, grab U projection, and we should find it not only in the shaders but also here. It's interesting, it's an optional, look at that, and still you can somehow access this from a vertex shader. Interesting. See? But that's super interesting, because if you ever want to learn how this works, you can probably just learn it from looking at the code here and maybe hacking on Doom a little. So get your transformation matrix. Oh, and here you basically forward the player in a shader. Amazing. Gee, but you have to understand the business with matrices. And that should be easy. Transformation matrix by a vector. I think that just advances the Matrix somehow, I don't know. Okay, so that does the color here, huh? Hue palette, hue texture, hue tile band size. This is something I've seen in code as well. Tiled band size. Yeah, add constant. So this is basically where these variables are set up for you. Oh. Here, this is shader set uniform mat 4. This is where you basically bring in the values into your shader. Nice. Okay. And then you do some computation with pi. Yeah, that's the sky, not to forget, so that has to loop somehow and whatnot. And at the end, you set a color. Okay. So what else? There's a sprite and static. Static might be the walls and stuff. So how does that work? That's the vertex shader. Which will... What can it do? Num frames. Okay, so it can be animated somehow. I don't know at all what this does. I don't see anything in here. But I didn't expect so either. You have light handling. You can just set up a... I don't know if that is something that the graphics card does for you. Or, no, wait, I think here's where you compute the positions of stuff, and then in the fragment shader you use them, huh? So we have to look for the vlight variables. I think that's the input stuff, that's maybe the output stuff. So the vlight, see? That's flat in. That's the flat out, sure. So that's what we produce. Atlas UV, title size, and here we take this as an input and use it to compute the shading. That's very nice. So that's cool. Usually you would, previously Doom would do that on the CPU, obviously. And now you just do it on your GPU. Much faster and more efficiently than the CPU could do it. Nice. Honestly, when you see that, you wouldn't ever want to work without a fragment and vertex shader anymore. And that's how I see it as well. So I guess if I should ever do these kinds of things again, I would just get into the vertex shader business and try to make it work, even though I have the feeling it's quite a different beast. Even though that's just C, right? It's nothing special. But yeah, you have to understand your math. Okay, so then we have sprite. Let's see, just for completeness, what the vertex shader does. And I don't know what the layout. So maybe we get some sort of structure and we access the individual structure fields and then assign it to field variables or something. Yeah, that's probably a standard function of any vertex shader. All right. Of any OpenGL vertex shader. Let's have a look real quick. OpenGL, vertex, shader, and layout. Layout qualifier. GLSL, okay. See, that's it. Can have layout qualifiers associated with them. Layout qualifiers affect where the storage for a variable comes from, as well as other user-facing properties. Okay. Okay. Something along these lines. So what do we do here? For the sprites, if it's a static sprite, you just have one position basically. If it's a non-static, you compute some animation properties, then you, I don't know what that would affect. It should in the end affect some position, but that seems to be a UV position. Oh no, wait, at the end you get a position indeed. Yeah, it's probably also, I don't know how that is done and how it's projected. I mean, the fragment shader then does the actual rendering. Yeah, I've no idea how this works. And this must be done per pixel somehow, huh? Per pixel that you want to render. And yeah, really interesting, but nothing I could, understand right now, unfortunately. But good to know that code like that exists. Yeah, then we have word reading. I mean, there's so much to look into here that is interesting. But considering you're already 40 minutes in, I say, well, we have seen a little bit. It was fun. I could jump to level 9. Oops, look, there's an unchecked axis here to our vector of levels. So here we go. Sprites! Cool! Oh my god! Now they're there. I didn't do anything. Awesome! And it looks the way it once should look. They always face you. Great. So sneaking up on these guys is impossible. Man. So many guys here. Gee. Let's place them right and left and on the other side. Nice. I don't know why the first level didn't exhibit this. These are constantly placed in shadows here, huh? To confuse you. Okay, so that's the red door. That's one of the last. If you follow this path, we should get to the end at some point, huh? Where's the end? Ah, come on. There must be the end somewhere. Ah, that's the yellow key. That's the one we just picked up, basically. And now there should be the end at some point. No, we always end up there. Here's the red one. Here's another red door. That's the one we just picked up. We have been here as well. Probably some trap is being set up. Oh, look, there is a secret passage here. Damn it! Let's go out of the level and maybe find the exit that way. It very well managed to confuse me. Exit, where are you? Down there, maybe? No, that's a lift. Ooh, whatever that is. Okay. It's fun and great that I see sprites finally. Oh, that's where you come from, yeah. And yeah, you should definitely have a look. And there's so much more that could be done. You could do sound. Of course, you could finally understand the code, implement some fancy features like filtering and maybe, that kind of stuff. But anyway, thanks for watching and have a great day.